Here we have an exercise where we're asked to find values of a and b that make a function f continuous everywhere. And our function f is piecewise defined. We have that f of x is equal to x squared minus 4 over x minus 2 if x is less than 2. Ax squared minus bx plus 3 if x is between 2 and 3 inclusive at 2. And it's equal to 2x minus a plus b if x is greater than or equal to 3. Note that our definitions are rational, polynomial, and linear. And we know that rational, polynomial, and linear functions are all continuous on their domains, so we have no question about the continuity of f except where x is equal to 2 and where x is equal to 3. Now we know that f is continuous at 2 if the limit as x approaches 2 of f of x is equal to f of 2. In order to find f of 2, I'm going to go ahead and note that we can factor the numerator into x plus 2 times x minus 2. The denominator is x minus 2. That divides out. And so we're left with x plus 2. As long as x is not equal to 2, we're going to figure out what f of 2 is by finding the limit as x approaches 2. But note that if we're going to have a limit as x approaches 2 of f of x, that means that the limit as x approaches 2 from the minus side of f of x is equal to the limit as x approaches 2 from the positive side of f of x. We're going to make heavy use of that. So as x approaches 2 from the minus side, we have this rational definition. As x approaches 2 from the positive side, we have the polynomial definition. So let's look at the limit as x approaches 2 from the minus side of f of x. That's going to be the limit as x approaches 2 from the minus side of the function definition where x is less than 2. The reduced version is x plus 2, and that has a value of 4. Because for a limit to exist, we must have the left-sided limit equals the right-sided limit. That must equal the limit as x approaches 2 from the positive side of f of x. And that's going to equal the limit as x approaches 2 from the positive side of ax squared minus bx plus 3. That equals 4a minus 2b plus 3. So we have the limit from the left is 4. The limit from the right is 4a minus 2b plus 3. So we know that 4a minus 2b plus 3 must equal 4. Cool, that gives us one equation. We need two equations because we have two unknowns, a and b. Now what I'd like you to do is I want you to examine what should happen when x is 3 for these other limits, and then go ahead and solve for a and b. Pause the video, do that, come back when you're done. Right. So f is going to be continuous at 3 if the limit as x approaches 3 from the minus side of f is equal to the limit as x approaches 3 from the positive side of f. And so for the ax squared minus bx plus 3, I substituted 3 where I saw x, so I have 9a minus 3b plus 3. And for the 2x minus a minus b, I substituted a 3 in place of x, so I got negative a plus b plus 6. And collecting like terms gives me 10a minus 4b equals 3. Combining that with the previous equation, in which I've also collected like terms, gives me a system. So I have 4a minus 2b is equal to 1, and 10a minus 4b is equal to 3. And eliminating b and then solving for a and back substituting gives me that a is 1/2 and b is 1/2. Now that's the end of the problem, but we're not quite done with this. So suppose we said that a is 1/2 and b is 1/2, then I would have expressions for the first function, the second function, the third function. Of course, x squared minus 4 over x minus 2 wouldn't change, but for the second definition here, I'd have 1/2 x squared minus 1/2 x plus 3. And for the third one, I'd have 2x, because the halves would subtract out. So I have this in a graph, which is kind of a mess. But you see we have a black function for the rational, a red or black graph, a red curve for the polynomial, and a blue curve for the linear. And now I'm going to clean this up so it's not quite the mess that we see right now. Now I've restricted the domain, and the rational function only applies, or the rational definition only applies when x is less than 2. So there's the black part. The quadratic or polynomial applies only when x is between 2 and 3, including 2 but not 3. That's the red part over here. And y equals 2x applies when x is greater than or equal to 3. That's the blue part right here. And what we can see is we have a Frankenstein graph. It's a piecewise defined function made up of 3 different functions, but they meet up at 2 and at 3, or at x equals 2 and x equals 3. That makes this function continuous, and those values that we found ensure that that's the case.